Hello, and welcome to our video on the inverse Fourier transform. We begin with a new concept. For a function f from the reals into the complex plane that is locally integrable, we define the principal value of f on R to be the following limit. PV, integral minus infinity to infinity of f, is the limit as R goes to infinity of the integral from minus R to R of f, if this limit exists. So f is locally integrable. The integrals minus R to R on f always exist. Maybe this limit does exist, maybe it doesn't. If it does exist, we assign its value to the symbol PV integral minus infinity to infinity of f. Note that I'm not saying here anything about the existence of the improper integral from minus infinity to infinity of f. Rather, I'm bundling the integral symbol together with the letters PV to denote this special limit. And of course, this is exactly how we always want to be able to calculate the regular improper integral of f, but we know that just because this limit exists, that doesn't mean that f is improperly integrable on R. For example, the principal value of the integral from minus infinity to infinity of x is equal to 0. Because x is odd, so those symmetric integrals, integral minus R to R of x, are all equal to 0. But we know very well that x is not improperly integrable over the whole real line. However, from last week, we remember that if f is in L1 and absolutely and therefore ordinarily improperly integrable, then the improper integral from minus infinity to infinity of f is equal to the principal value of the integral from minus infinity to infinity of f. So if the improper integral exists, then you can calculate it with this nice symmetric limit. If this nice symmetric limit exists, that may or may not imply that the improper integral converges. Here's how we're going to use this tool. Say we have a function f that's in both L1 of R and C1 piecewise, so f is absolutely integrable and piecewise continuously differentiable on R. Then first, the principal value, the integral from minus infinity to infinity of f hat of k, e to the I kx dk, exists for all x in the reals. Let's look at that for a moment. If f is in L1, then we certainly know that f hat is defined. But we don't really know anything about the integrability of f hat. In fact, in examples from last week, we saw functions f in L1 whose Fourier transform f hat was not in L1. But here I'm saying that if f is in L1 and C1 piecewise, then at the very least the principal value integral exists. And in this principal value integral, the dummy variable of integration is k, which morally makes sense because k is what we use for the variable of the Fourier transform, and now x is a parameter. And we also note that I have e to the I kx here, not e to the minus I kx here. So this principal value integral exists, and moreover, I have the identity f of x plus f of x minus over 2 equals 1 over root 2 pi times the principal value of the integral from minus infinity to infinity of f hat of k e to the I kx dk. So on the right, I have this principal value integral times a 1 over root 2 pi, and on the left, I have the average of the left and right-hand limits of f. So remember, f of x plus is the limit as x goes to the right of f, and f of x minus is the limit as you go to x from the left on f. So this looks very much like an inversion formula for f in terms of f hat. On the left, I have values of f, and on the right, I have stuff involving f hat. Let's pull back a little and give something a new name. The inverse Fourier transform of a function g from the reals into the complex plane at a point x in the reals is g check of x, or f inverse on g at x, which we'll define to be 1 over root 2 pi times the ordinary improper integral from minus infinity to infinity, g of k e to the I kx dk, whenever this integral exists. So in the previous slide, I had an integral that looked like this, except it was the principal value integral. Now I'm saying that the inverse Fourier transform is the pure improper integral, no principal values, assuming the improper integral converges. So what does this tell us? The inverse Fourier transform really inverts the Fourier transform if you believe the theorem on the previous slide. Because here's what happens. If you have f in L1 and in C1 piecewise, so that we can use the identity on the previous slide. And you also take f to be continuous, so f of x plus and f of x minus are the same. And if you take f hat in L1 of R, then you get the following things. You get f of x equals f of x plus f of x minus over 2. That's just agreement of the left and right hand limits by continuity. And this is equal to 1 over root 2 pi times the principal value of the integral from minus infinity to infinity f hat of k e to the ikx dk. That's the identity from the previous slide. But this, happily, is equal to 1 over root 2 pi integral minus infinity to infinity f hat of k e to the ikx dk, because I'm assuming that f hat is also in L1. And in that case, the improper integral and its principal value are the same. And that is the inverse Fourier transform applied to f hat at x. So with a few extra hypotheses, non-trivial hypotheses, L1 piecewise C1 continuous, and f hat also in L1, we get f is equal to the inverse Fourier transform on f hat for all x. On the other hand, even if your Fourier transform f hat is not in L1, this inverse identity, f of x plus f of x minus over 2 equals 1 over root 2 pi principal value, always holds. So there will be some examples, we're going to do one in a moment, where f hat is not in L1, and still we can fool around with the inverse Fourier transform to figure out what f is. So don't be too attached to having f hat in L1, because as we know from examples from last week, that's not always going to happen.